All right, let's do it. Let's go to this problem here. Remove duplicates from a sorted array. Here's the link to that problem. There's a chance to get there. All right. Cool. Here we have given an integer array called nums, sorted in increasing order, aka non-decreasing order. I don't know, I'm not sure why the purpose for the double negative there, but increasing order or from smallest to greatest. Remove the duplicates in place such that each unique element appears only once. The relative order of the elements should be kept the same. Since it is impossible to change the length of the array in some languages, you must instead have the result be placed in the first part of the array, called nums. More formally, if there are k elements after removing the duplicates, then the first k elements of nums should hold the final result. It does not matter what you leave beyond the first k elements. Return k after placing the final result in the first k slots of nums. Do not allocate extra space for another array. You must do this by modifying the input array in place with O of 1 extra memory. And then the judge 0, which is the code they use to run the answer, is going to do this. That's fine. If all assertions pass, then your solution will be accepted. Well, that's good. Okay, now here it gives us some examples. I'm going to start typing up here a little bit. Where are these examples? So we can see what that looks like. So they say, okay, you could get 1, 1, 2. Now we bring out our pointers and we say, okay, so if the leading pointer is pointing to the same thing as this one, then we want to get rid of it. But we don't know exactly where to move it. So let's instead revisualize it as our lagging pointer says where we want to move it, and our leading pointer says when you find a new number, swap these two. So this becomes 2, and this becomes 1. And then this one moves up, this one moves up, and this one moves up, and we are off the map and we're done. Let's pick a larger one here, this one. Oops. Okay, so this says, if and when we find a new number, then let's make a swap. So, hey, here's the same number. Here is a new number. Okay, when we find a new number, we want to move this pointer up 1, and we want to swap these two. This becomes 1, this becomes 0. And now we keep going without moving this one up this time, checking. Are they the same? Same, same, same. Different, different. Okay, when they're different, move our lagging pointer up and swap these two. This becomes a 2. This becomes a 0. And now we keep going. 2, 2, same. 3, 2, different. Move this one up. Create here a 3. Move over here, what was it, a 0? Forget, 1. This becomes a 3. This becomes a 1. And now we're ready to move up again. We see another 3. And finally, we see a 4. We're going to move this up. We're going to create a 4 here. And then this becomes whatever that was before, 2. They said it doesn't matter what you leave back here, so we don't have to worry about that too much. Then, very importantly, they want us to return k, where k is the number of unique elements. So k is going to be whatever our lagging pointer is, plus 1, because remember, it's pointing at the index. So it's pointing at 0, 1, 2, 3, 4, but we need it to count the number of them, which is 5. It's a lot. We'll get it. Who already has a solution? Maybe someone's like, boom, I already solved this. Good for you if you do. Good. I'm happy to hear that. Let's go through it nice and slowly. So we say let lagging pointer equals 0. Then for let I equals 0, I is less than nums.length, I plus plus. Okay. Now we care if nums at I is not the same as nums at lagging pointer, then we're going to do something. And otherwise, we need to do anything? No, I don't think so. We just need to move I up. So what are we going to do? First thing we're going to do is move lagging pointer up by 1. Then we're going to set a temp variable to hold num at lagging pointer. Then we're going to set num at lagging pointer to num at I. Then we're going to set num at I to temp. Then we need to return the number of unique elements. Here, give me 1 second. Go ahead and start coding if you'd like. Okay. Do something is not pseudocode. That's just to remind myself to do something. Here, though, we have most of what we need. So the first thing we want to do is move our lagging pointer up. Remember that lagging pointer is a integer. That's what we call those. So we can just do plus equals 1, plus plus, however you'd like to just add 1 to it. Then I don't really think we need this temp variable, but it's a really good practice to get in where we say temp equals nums at lagging pointer. So we can do something with it later if we'd like to. Okay, then we say nums at lagging pointer equals nums at I. And then same, nums at I equals temp. All right, now when we finish, our lagging pointer will be on our last unique number. So we can just return lagging pointer plus 1. Because again, lagging pointer is the index and we need the number of elements. So it'll be the index plus 1. And with that, let's give it a try. Great. So look at our console here. Okay, let's run our test cases. See if this works. Good, it does. Take a look here. Let me just console log so we can see better. Let's do console.log nums. Yeah, here you can see how we're not actually shortening the array the way that LeetCode is kind of making us believe we are. We're just swapping things as we go. And with 2, we can see it even better. Our result here is 0, 1, 2, 3, 4, with all of these numbers just kind of thrown in the back here. After we had this kind of input, and now we've got all our unique elements up front here. Let's write our own test. So I don't know if you're not familiar with this, you can click on test case and then click on the little plus icon. It will open up room for you to write your own tests here. So we could say we want 1, 1, 1, and then 2, 2, and then 3, 3, 3, 4, 4, 6. So we expect to get 1, 2, 3, 4, 6, which is 1, 2, 3, 4, 6, 5 unique elements. We should be returning 5 with an array that has all of the unique elements up front. Here's our case 3. Hey, we see that we do return all of those unique elements, 1, 2, 3, 4, 6, which is great. And here's what we're actually doing to the array. We've got all our unique elements up front, and then we've taken all of our duplicates and just thrown them in the back here in no particular order. Very good. Any questions here? Let me bring up that code one more time. Let me get rid of my console log now. Who knows what the runtime of this is, or the time complexity? How many loops? How many loops doesn't always tell us the answer, but go ahead, Herman.
I might be wrong, but is it just a runtime of n?
Yeah, just a runtime of n. That's correct.
Yeah, because it only needs to iterate once, and it's just holding on to that number, and it's just inserting it, so that doesn't really add anything, right?
Correct. Yep. It's just going through once, and we're just bringing up our lagging pointer. Typically, using 2 pointers is something that allows us to work much more efficiently than if we tried to sort of run ahead and then go back and forth, and that would be more like a runtime of n squared. All right, let's make sure that we're passing the full problem here. Looks good. I don't put a lot of stock in these things, but we're I don't know, I guess middle of the, here we're doing quite good, beating a bunch, and then here we're kind of middle of the pack. But good. I think that's a nice use of how to use 2 pointers. Now you see though, through these 3 pointer problems that we've done, each time the logic is a little bit different. So you have the concept of 2 pointers and making sure you're comfortable with that pattern. But then you also need the flexibility to say, okay, well, it typically is the case where I have a lagging pointer and a leading pointer. But I can't know for sure how I'm going to move them or what the condition is by which I'm going to move my lagging pointer up. There's also the possibility that we have 2 pointers starting from opposite sides of an array, like the first element and the last element. We would do that more with binary search, for example, in which case we will put them at the start and the end and then move them as we go. So pause again for any questions. We'll do one more problem here. Okay, should we do another LeetCode problem or should we do binary search? Anybody have a request? That was not me. I was trying to search code. Or do both. Here's binary search on LeetCode. I guess we'll do this. If we finish this, then maybe we'll get to one more problem. All right, so here's the URL. Okay, binary search is a pretty classic 2-pointer problem. Let's see, given an array of integers called nums, which is sorted in ascending order, and an integer target, write a function to search target in nums. If target exists, then return its index, otherwise return -1. You must write an algorithm with an O log n runtime complexity. Yeah, okay. So let's talk about this real quick and then we will do it. Let's grab an example here. Here's our array. Now we're looking for a number 9. So if we wanted to just do this in n time, we just look at each one. Is this 9? No. Is this 9? No. Is this 9? No. Is this 9? No. Is this 9? Oh, yep, it is. Done. We're done. If we said we're going to look for 13, great. We go back to the beginning. We say, we look. We looked at all of them. That's n. That's why we call that n. And we say no 13. We're done. Cool. But we need something that is log n. If you've been in class with me before, you've heard me go over this. What the hell is log n? Usually I don't say hell though, I just keep it, or G. Now we have the PG version because I put in hell. Look, I'm even going to capitalize it. What the hell is log n? Log n just means how many times do I cut something in half to get to 1. So if I said, what is the log n of 10? All that means is how many times do I cut 10 in half to get to 1? Well, 1 time is 5, and then another time is 2.5. But for the sake of easiness, we're just going to round up. So that would be 3. And again is 1.5, but again, we're going to round up. So it would be 2. And then again is 1. So I cut it 1, 2, 3, 4 times. That is log n of 10 is equal to 4. Okay, well then how about 100? Well, from 100, I get 50. From 50, I get 25. From 25, I get 13. From 13, I get 7. From 7, I get 4. From 4, I get 2. And from 2, I get 1. And now I just count them. 1, 2, 3, 4, 5, 6, 7. Log n of 100 is 7. Okay, let's try something more complicated. How about 1344? You take a minute and you tell me the log n of 1344. Everybody got it? 20 more seconds. Put it in the chat, folks. $670. What is that? It's 22, 72. 650. Yep. 672. 336. 168. Feel free to just correct me if I'm doing this wrong. 5084. 42. 21. 12. 10.5, 11, sorry. 11, 6, 3, 2, 1. I hope I didn't make any mistakes, and we just count them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the log n of 1344 is 11. And you can already see in just a few numbers how 10 was 4. 10 times 10, 100 is 7, not even 2 times 4. And then more than 10 times 100, 1344, we've only gone up to 11. So we can see how even when the input grows quite a lot, even if I have an array of almost 1,350 things, my log n is still very, very efficient. Whereas if we had n, we would have gone from 10, 100, 1344. I will try very quickly if I can do this. Can I do this? If I do 10 or 100 or 1344, and then I say on this axis here, what is O n for these things? And it's very simple because it's the same. It's 10, it's 100, it's 1344. And then down here, I say, okay, what is O log n? Only this would be easier if I had somewhere more proper to draw notes, I suppose. Could have made my life easier. And that we said was 4 or 7 or 11. So you see how much more efficient this log n is of these things. All right, so that's what 2 pointers is going to do for us here. Let's comment this all out. Let's write up. Let's keep this for a second so we can sketch it out. So with binary search, what we're going to do is we're going to set our pointers at the first position and the last position. And then we're going to look for the number in the middle here. And we're going to check if it is bigger than or less than or exactly what our number is. So if I say, okay, this pointer is at 0, and this pointer is at 0, 1, 2, 3, 4, 5. Then I want to find the middle, 0 plus 5 divided by 2. 0 plus 5 divided by 2 equals 2.5. Now we need to decide if we're going to round up or round down. Let's round down. Why not? So it's math.floor of 2.5 is equal to 2. So now we find our element at 2, 0, 1, 2. Okay, it's 3. We ask ourselves, is that bigger, smaller, or equal to our target? It's smaller than our target. Therefore, we can move this pointer up to this plus 1. So 2 plus 1 is right here. And now we repeat the process. So now this is at 3. Now we do 3 plus 5 divided by 2. 8 divided by 2 is equal to 4. The floor of 4 is also 4. We look for element in 0, 1, 2, 3, 4th position. It's 9, it's equal, and therefore we return, we just return the index here, which is 4. If we weren't to find it, we would keep moving up. Once these two things meet, then we know that we're crossed. We know we've not found our answer. So let's just walk through this step by step. So we say let lagging pointer equals 0. Let leading pointer equals nums dot length minus 1. Then we find our midpoint. Let midpoint equals leading pointer minus lagging pointer. We need to make sure we use math.floor here. Or math.ceiling, we just have to be consistent. Math.floor, like so. Great. Now we say our midpoint can be a match. It can be greater than, or it can be less than. So we need to handle all of these conditions. Let's handle match first. Easy, easy. If nums at midpoint is equal to target, return midpoint. That means we've found what we're looking for. Else, if nums at midpoint is greater than target, we need to do something. Otherwise, it's less than. And we'll do that. So let me keep these organized here. Just going to put that there and then put this here. Good. Okay. If the number is greater than the target, it means we need to move our leading pointer down. So here we say leading pointer is equal to midpoint minus 1. Otherwise, we need to move our lagging pointer up. Lagging pointer equals midpoint plus 1. Good. Now, there's a couple different ways we can do this. Once we've done this here, we might as well just call our function again if we want to do it recursively. So we could do that, or we could do it iteratively. Let's do it iteratively. If we want to do this iteratively, we need to put this whole thing in a while loop. While midpoint is not equal to target. Sorry, nums at midpoint. So we want to do return midpoint. We can, since we're checking for match here, we could just get rid of this here. Let me think about if I want to do this way. Let's change our logic here. Let's say this instead. Let's keep this. Let's just say while lagging pointer is less than or equal to leading pointer. And then here we return -1 if we don't find anything. Yeah, -1. Great. Otherwise, we'll return from inside of here. That's nicer. Okay. Then we need to take this here and bring it inside of our loop. We'll find our midpoint right here. Then we'll check. Then we'll move our leading pointer or our lagging pointer and we'll do it again. Yeah, it seems right. Let's walk through it. Always try and be very careful to walk through my code before I just run it. Let's see if we find any bugs here. So here's my example down here. Let me clean up just a tiny bit here. We can try and keep everything on the same page. Good. Okay. Lagging pointer set to 0. Done. Leading pointer set to nums.length 0, 1, 2, 3, 4, 5, 6 minus 1 index 5. Yep. Done. Okay. While lagging pointer 0 is less than or equal to leading pointer 5. Yeah, that's true. Okay. Let midpoint is leading pointer 5 minus lagging pointer 0. Oh, I see an error. Divided by 2. This is why it's important to walk through your code. I know you're much smarter than me, most likely, but if you ever have bad days, then you want to make sure we take the time. Okay, leading pointer 5 minus 0, that's 5. 5 divided by 2 is 2.5. The floor of that is 2. Good, we should get 2 here. Then we say if nums at 2, 0, 1, 2 here is equal to target. Okay, that's not true. Otherwise, if this number 3 is greater than target, that's not true. If it's less than, move the lagging pointer to midpoint plus 1. Okay, midpoint was 2. So we come to 0, 1, 2, move this to 3. 1, 2, 3. Come back to the top of our loop here. Check if lagging pointer is less than or equal to leading pointer. Yes, it is. Okay. So then we go back through this again. Here we have 5 minus 3 is, oh, I made a mistake here. This is plus. Another mistake, right? 5 plus 3 is 8. 8 divided by 2 is 4. Rounded down is still 4. Good. That's my second bug in my code. And then we say, is that number equal to the target? Yes, it is. So then we return the midpoint, which is 4, and we should be done. Good. Let's try a different one here where we're looking for 13, since that doesn't exist. And let's run that again. Starts at 0. This looks at 5. Good. Okay, going back then. Excuse me. We're resetting. So our lagging pointer is less than our leading pointer. Yes. Our midpoint is 5 plus 0, which is 5 divided by 2, which is 2.5. Rounded down is 2, 0, 1, 2. Looking at 3 here. Is that number equal to 13? No. Is it greater than it? No. Is it less than? Yes. If it's less than, move the lagging pointer to that plus 1, which is going to be here at 5. Good. Do it again. 5 plus 3 is 8. 8 divided by 2 is 4. Looking at 9, is 9 greater than or less than? 9 is less than. Great. Move this up to here. Okay, now they're pointing at the same number, 5 and 5. So we say, all right, is it less than or equal to? Yes, it's equal. Okay, we come down here. 5 plus 5 is 10. Divided by 2 is 5. Rounded down is 5. 0, 1, 2, 3, 4, 5. Looking here, is that equal to or less than? It's less than. Therefore, what do? We do lagging pointer equals midpoint plus 1. This one comes up here now. And now this is no longer true. Lagging pointer is greater than leading pointer. Therefore, we should return -1. Good. Let's check one more thing before we're done, which is -5, something that's on the other side here. So we'll reset here, go to 0. Okay. Let's do the same thing. Hopefully it's the pattern is starting to become a little more clear. Our midpoint is 5 plus 0 divided by 2, 2.5. We're looking at 3 here. 3 is greater than -5. That puts us in this condition here. Leading pointer comes down to midpoint -1. So we're going to come down to 0, 1, 2, to here. Did I mess that up? 0 plus 5, 5 is 2, 2, 2, 2, 2, 2, 2. No, we're already down to here. Great. This is 1. We do it again. 1 plus 0 is 1. Divided by 2 is 0.5. Rounded down is 0. Now it's looking at this. That's also bigger than -5. This comes down here. Now this one has passed this one, and we should return -1. Great. I think we're ready to run our tests. I feel pretty confident in this code. Any questions here? Okay, let's run the test that they already have for us. Good, looks good in both cases. Let's create a new test case. So actually, let's just do this like we had, but then with a bigger number, should return -1. Great, let's add another test case. And we're gonna do this one on the other side with -5. Great. We could do some more tests, but I think that's pretty good. Let's go ahead and submit that. See if we're passing all cases. Beautiful. And there it is. We've got it. Okay. Where's our code? Here. Still getting used to this new layout for LeetCode. Okay. Good. Let me pause and take any more questions there, and I will give you I think I have a link here for another one. Go ahead, Herman.
Yeah, I have a question about binary search. Isn't
Mhm.
it just possible to just make a clause since we already know that 13 is like the largest element in it? If we see that the leading pointer, which is like the maximum, is like less than that 13, can't we just automatically say it's not found, so return -1? Or does the leading and lagging pointer have to traverse the array and then make sure that the 13 is not in the array, then return -1?
That's a good question. We could do something like that, and it may be worth it. We could add like a guard clause up here, right? That says if target is greater than the last number or less than the first number, then for sure it's not there, right?
Hmm.
That would work for that. You just want to be careful that you don't overlook a case. I don't have any problem with that, with your suggesting. How do I edit? Here we go. You want to be careful about a case like this where we're looking for 8, because then we still need to make sure we run through all the steps, right? Like 8 does fall in this range, but it's not here. So anyhow, you certainly could save some time. It's so efficient that it may not be worth it, but there's nothing wrong with what you're describing. It would definitely work. And
Gotcha,
it may
gotcha.
save
It
us
might
a
be a
little
more
bit of
messy
time.
implementation, I suppose.
I'm not even sure that would be the case. We would just say here, we just add a guard clause that says if target is less than nums at 0 or target is greater than nums at nums dot length -1, return -1. It's more just a guard clause. I don't think it's any more messy. And then we see if, if we're squeezing out much more. I don't know what it was before. What's here? Well, look, now it beats 66. So, hey, that's something.
Nice.
Again, I'm not like, I always find these. Oh, now it beats 99.5. I find these metrics like very, very unreliable here, but I can't. Yes, this adds 2 more operations for every time you run the function, though sometimes it's going to save us a bunch of operations since we don't have to do this here. So it's a good idea. I think it's perfectly nice. Just make sure you don't overlook that case where a number does fall in the range but is not present in the array, in which case we still need to run through these steps here.
Gotcha. Thank you, Jordan.
Yeah, of course, good idea. Love ideas like that. Look at that, beating 99.5, amazing. It just jumps all around. Like I really think it changes a lot based on either my connection time, my internet connection, or their server, what their server is doing. Okay, we're not going to do this one now, but here is another problem. I'll put this in the chat and you guys can grab it and work on it on your own. Yeah, this one is different, similar, but different. Another good one to practice with 2 pointers. And I was looking and I'm going to do something that I don't usually do and refer you to this practice here. Our friend over at LeetCode has nice problem sets that I don't yet have for LeetCode problems, grouped by concepts here. So of course you'll get points on CodeTrack regardless, but if you want some more stuff to practice on, you've got a nice list of problems here. Remove duplicates from sorted array. This is the one that we did today together. Merge sorted array, reverse string, minimum difference, valid palindrome. Yeah, I don't know why he doesn't have binary search here. Maybe he has search. Oh, he has binary search down here. Sure. And we did this one today too, binary search. And then we did a couple that I made up for us just as intro problems to this concept here. So keep getting some practice with that, get comfortable with it. And that brings us to the conclusion of our class for today. Does somebody have any other questions? Great. Okay. Well, have a great weekend, and I will see you all next week. You're all welcome.
Enjoy your weekend,
All right.
Jordan. Thanks for the class.
Okay. Thank you. Talk to you soon. Bye.